today we're going to concentrate. This session is about HTC services, and we try to make good use of the OpenStack cloud resource. There are going to be three of us. I'm more like a pseudo person that I represent, part of like Vinay, he could not be here, and Chris Hill at MIT, who really started up this project. And today we have myself. My name is Pianai. I'm from the Massachusetts Open Cloud at Boston University. I'm a director of engineering there. And we also have Raju, who is our graduating MS student from Northeastern University. And then we have Lucas Yu, who is an engineer at Mass Open Cloud. So let's get started. This is an outline of what we're going to talk about. We're going to talk about motivation, why we even doing this at all, why we spend resources on this. Goals from the scope after we invested the problem we try to solve, and then implementation, how we do it, how we done it. And then we will have some demo, followed by future works, and as well as summary. So now I'll hand it to Raju.
Sure.
Go ahead.
Thanks, PNA. So I'll begin with our idea of HPC and cloud convergence. So why do we believe these two can be brought together? So if you look at the HPC clusters, they always have infinite demand for resources. The job queues are always piled up, looking for more and more resources. So no matter how much resources you provide, like they're still looking for more resources, and even after this, if you go to the subscribers, they still have some jobs to submit and pile up the queues. OpenStack Cloud or any cloud, on the other hand, if you see, they are generally designed for peak workloads, and they tend to stay underutilized most of the time. So the big question that we had was, can these HPC jobs use the idle cycles on the cloud, and can they give us a better throughput and a better utilization? An important point to focus here is this convergence should not impact the actual on-demand cloud users, because all we want is to share the underutilized resources to the opportunistic workload and not impacting the actual workload. Another point here is, if we look at the multi-node HPC jobs over virtualized clouds, they're still not there. They're still not mature enough to run. On the other hand, if we see specifically the virtualization on the compute end, they are doing great. They are quite as fair enough and working good at par with the bare metal. So for the premise of this project and the talk here, we'll focus on single node jobs. So when we started working on these aspects, sure, yeah, sorry. Working on these aspects, we carved out a few set of goals, and I'll quickly take you through. So the very first goal is to manage. We need some service that will manage the sharing of resources between the actual cloud user and the actual cloud workload and the HPC clusters that we're gonna put across. So that should share the growing and shrinking of the HPC clusters based on the resource utilization. If the cloud is underutilized, it should grow the cluster, getting in the virtual nodes, put it into the Slurm cluster or an HPC cluster, and shrink it when the utilization goes up. Another goal that we had is, if we have to shrink a cluster, it should be done in a workload-preserving fashion. You can just terminate a VM, you may lose the job, but there is no point investing the idle cycles, the compute cycles into it, if we cannot save those cycles. So we have to do it in a workload-preserving fashion. And now this is all good for the HPC users who are familiar with working on these compute clusters. However, we are working to provide a simpler user experience to the cloud users who are not very much familiar with the compute clusters. And we are trying to do this by integrating this computing cluster into as a new interface to an existing scientific gateway that we have at MOC that's called Giji. and Lucas will speak more on this. So let's begin with how we carved our goals here. If we look at the traditional HPC cluster, it generally has a bunch of compute nodes and a controller, and that is driven by some kind of a workload manager, which is for us Slurm in this case. Apart from that, it has some other compute services and support services like DNS servers or shared file systems that helps in seamless integration across the compute nodes. As I mentioned, these clusters are almost completely utilized, and we want to grow these clusters and as and when the workload comes in over the virtual machines. So there could be two of the scenarios. We could have a co-located HPC cluster and an OpenStack cluster in the same data center. And we could see here like the HPC cluster on the left is completely utilized. All the nodes are running some workload. On the right, we could see there are OpenStack nodes which are highlighted with green, and they are running the cloud workload, like on-demand workloads, and most of the resources are idle. So if the resources are idle, we could expand these. We could expand the HPC cluster using these virtual nodes. Another aspect could be, since we are using everything, since we are trying to expand it over the virtual clusters, it could be a cool idea if we could host this HPC cluster over the OpenStack cluster, having all the instances as virtualized nodes. So in order to do this expansion, I'll take you through our very first goal, which was managing the sharing of resources between the HPC cluster and the on-demand cloud users. So let's see here we have a Slurm cluster on the left, which has a controller and a compute and bunch of compute nodes. We have parallelly we have on-demand virtual instances, of which some are utilized and some are lying idle. We have Monasca, the OpenStack's monitoring service that is monitoring the resource utilization of the entire cluster. Now let's assume all the compute instances within the Slurm cluster are completely utilized. They are running some workload, and a new job comes in. Now to execute this job, there are two ways. Either it should wait for the jobs to get completed, and then when the resources free up, it could begin its execution. Or there is a service that could grow this cluster, get the idle instances from the existing cloud, and add it to this Slurm cluster. So let's say we have a service that interacts with Slurm and fetches the resource utilization metrics from Monasca to figure out if we have the required resources to create a new compute node and add it to this cluster. If it figures out it has, it calls some kind of provisioning and configuration tool that will configure this new instance, it will provision it and configure it in the new instance. Once the new instance comes up, it will respond back to the cluster that I'm up and running and I'm ready to accept the jobs. And the controller will allocate the job to the new compute node that came up. So in this way, we end up growing the cluster by adding a virtual node to it. Now, down the line, if we figure out, okay, the utilization has gone up and there are more on-demand cloud users coming in, and this service is continuously looking into the Monasca metrics, and it's figuring out what is the current utilization. And now there is a specific threshold that is defined with this service, and it figures out if the utilization has gone beyond the threshold. It needs to get the virtual instances that were added to the HPC cluster. So it just pulls back the instance and return it back for the on-demand cloud users. Now we could have done it by just terminating this virtual instance, requeuing the job. But in that case, we'll end up losing the compute cycles that we already invested. So this leads to our second goal of shrinking the HPC cluster in a workload-preserving fashion. In order to do this, what we do is we just suspend the instance using Nova API on OpenStack. Now, when you suspend the instance, Nova creates a snapshot of that very specific virtual machine keeping all the process states. And then in the next step, it stops that virtual machine on the hypervisor so as to free up the resources. So in this way, we end up keeping the states of the job intact, and we also end up releasing the resources which could be used by other virtual machines or other workload that comes in. Now, doing this, another problem comes in as suspending the virtual compute nodes, it unsettles the Slurm, the workload manager in this case. So if we look at the traditional Slurm behavior, what happens is a compute node, so a controller, it is always pinging to all the compute nodes that are there to fetch the status of that specific node. And if any of the compute node that doesn't respond to this ping, the controller figures out, okay, I've lost this node, and it'll mark that node as down, and it will remove all the allocations that were there, including the jobs and everything. The jobs get requeued, and you end up losing the cycles that you already, and whatever the processing of the job was done. So in order to get over this and preserve the state of the very specific node that we suspended, we added a new node state into Slurm called suspend. Now, when a controller finds a node with this suspended state, it stops pinging, or it skips that specific node during the cycle when it pings all the nodes. And it won't, and in Slurm, like the controller, it marks the node state as unavailable for allocation of the jobs. So no new jobs or no jobs on the queue, they get allocated to this very specific node. So eventually it isolates the node, and then you can get rid of it. And the Slurm will, however, it will keep the states intact. It doesn't know where exactly the node is, because it's no more trying to reach out to that very specific node. So we can then suspend the virtual instance that was acting as this node, and later on restore it as and when we have the resources available. We proposed this very specific design into the Slurm user group a few weeks back, and we found we have other users with the similar ideas as well. So very soon we might have this as an enhancement into Slurm. And apart from this, we made another change. We exposed few of the Slurm APIs as REST APIs, so that this service could fetch the required information from Slurm and make a decision on whether it has to create or remove create an instance, or suspend or resume an instance. And this service here is, for this service, we used an OpenStack service called OpenStack Watcher, and Pia and I will speak more on this.
So, what you have gone through from HPC's perspective, how things would work. Now let's come back and look at what the OpenStack service we used to make this happen. So how many people know anything about OpenStack Watcher? Anyone? One, okay. Oh, it's going to be interesting. Okay, so Watcher is basically a service, and matter of fact, it's in a Big 10 service. You can look through the wiki page that I point out there. But one thing that we found is that Watcher is very flexible, and it provides some platform, and starting by auditing the cloud itself, and give you a way to monitor the cloud and take action. And those actions are customizable, and that's the key things, and it's also multi-tenant cloud. A good real-life example of this would be with the Giji project. And this is back a couple years back. You look at the time a year back. They employ the OpenStack Watcher in Giji, which is an EU project. Talk about green network and data center environment. It's really remarkable and interesting. So they use Watcher in a way to help reduce the energy of deploying the OpenStack cloud. In this case, the pointer is there. Feel free to go there and check it out, the blog. So how do we use Watcher in our scenario here, in our project? Cloud utilization, we're starting off, we're setting a threshold when we want to start to borrow
or leasing the compute from OpenStack, and when we want to give it back to OpenStack. The threshold we set is 50%. This is customizable in Watcher. And we just pick 50% just, for our POC, make sure this just sounds like a good idea to us at the time. In Watcher, you can also set to see your utilization, your action plan would be continuous or just one time. We set it to be continuous. We say we want to monitor our cloud continuously. And the value we set there, 10%, to see, it's almost like clone job, right? If anyone know anything about Unix or Linux, it's similar ideas there. And we use, in our environment, we use Monasca to monitoring both CPU and memory. Again, in our strategies there, we only use CPU and memory. And in the future, we might expand that. This is just the first version that we have. Okay. All right, so thank you. The strategy that we set up here and say, what do we want, when do we want to grow? And when do we want to shrink the HPC cluster? If less than 50%, we can do two things. We can resume the job that got suspended, as well as the node on the Slurm, or we can acquire new resource from the cloud, right? And then we create an instance, we inject whatever Slurm image that you need, tool that you need, and then we add that to the Slurm queue. And we have particular, we call Slurm OpenStack partition in Slurm management there. If it's greater than 50%, we know that the cloud end. We need to give resource back. What did we do? What do? We suspend the associate Slurm job being run there. This is a new code that Raju had mentioned that got proposed to Slurm user group. And then we also used Nova API to suspend the instant API. So let's look at all this in summarizing it, okay? We set our objective, we have a goal. What do we want? We want to run the HTC job, the high-throughput computing jobs. Focus on one job at a time. On the VMs by growing or shrinking HPC cluster. Now, again, this is the virtual HPC cluster that we create in the OpenStack cloud. And based on cloud utilization, the keyword here, cloud utilization, how do we find out? We use Monasca as monitoring tools. How do we get that? We aggregate all the OpenStack compute nodes and come up with across all the clouds, our clouds, and we set up the profile, say that that's our threshold, 50%. And then we plan, what do we want to do? Greater than 50%, we have certain actions we want to do. Less than or equal 50%, we're executing job. Then we apply it, right? Again, if it's greater than 50%, we want to suspend jobs. We want to suspend the VMs using Nova API. If it's less than 50%, it means that the cloud, our cloud, has more compute to share with the HPC cluster. And then what do? We resume the suspended job. Either that, if there's no suspended job, we go back, ask them, do you have any jobs for us to run? Then we create a VM for you, and then we run that job. We tell Monasca, we tell Watcher that we want to do this continuously, like cron job that I mentioned before. Every 10 minutes, we'll probe Monasca and say, where are we right now? What the cloud utilization level is? So we go around this cycle. Again, two keywords here, cloud utilizations, grow and shrink the SPG. Okay. Okay, let me just do this.
Okay, we're good enough. Yeah. Go ahead.
No. Okay, so thank you. So the last goal that we have, so I remember this cycle, right? This is exactly how things work. There's a lot of things happen behind the scene, both on the Slurm's end as well on the OpenStack end. And all this code we're going to be putting GitHub right now. And you folks are welcome to contribute or share, and we're going to move it further. And Raju is going to come up and tell us in the future works that we plan to do. Last but not least, Raju talked about HPC community, right? What about cloud communities? Someone like me, I am very naive about HPC and know the keywords and all that, but if you want to try out HPC cluster, you want to deploy, you want to see what Slurm is all about, we come up with some easy to use, simple, good graphical user interface we call Giji. And Lucas is going to be talking about that next.
Thank you, PNI. So let me go to the next slide. So Giji is a MOC project that has two goals. The first goal is trying to provide a simple-to-use user experience to our end users, who are mostly our researchers, who are not necessarily familiar with cloud concepts like setting up a private network. So another goal of Giji is we're trying to build this as a gateway to access to different MOC services, such as OpenStack and OpenShift. We had a talk in the Boston Summit about Giji, and if you're interested in, feel free to take a look in the YouTube. This is a screenshot that shows you about how we're gonna plan to provide this service. So eventually, an end user in our cloud should be able to submit a job, a HTC job with minimum know-how, and then the job will execute on the Slurm cluster. And then it will eventually provide a result back to here, so you can download the output file and see the result. I'm about to show you two short demos. Unfortunately, Giji won't be in this demo because it's still at early stage, but this two short demos should give you a quick overlook about how we're doing things right now. Okay. So the first demo here is about growing the Slurm cluster by adding VMs in the OpenStack. As you can see here, we start with no compute nodes in the Slurm environment, and then we submitted a job in the background. You can imagine this like submitted by the Giji, or you can just use the controller. You can just use the CLI to do this. So the job is at the pending state right now because it's still waiting for resources, and then it can be computed. We have this tool called OpenStack Watcher that it checks frequently, like, every 10 minutes. That's just the time we choose, but you can configure to another time. So the Watcher will eventually boot up a VM that will be configured as you can see here. The VM is booted here, and it will eventually configured as a compute node in the Slurm controller, Slurm cluster. Now the VM is booting, and you will turn to the active status here. But it takes time because it needs to configure this to become a compute node in the Slurm environment. But it will be really fast if we use a pre-provisioning image. It will take less time to do this. So you will see if I run another SQ here, which coming really, yeah, it's still in depending state right now. It should be, the job should be at the running. Okay, now we see the compute node is turned into the allocated state, and the job is at the running state right now. So this is the end of the first demo we're gonna show you. The second demo is about growing and shrinking the Slurm cluster based on the cloud utilization. So let's say we still have the compute node here that is available to compute jobs. And we submit a job in the background, and then it starts running because it has the available resources here. Then we increase the overall cloud utilizations, and eventually will exceed to the threshold we set up. And then you will see that the job will turn into the pending state really soon. So here just still showing you guys the job is running. Yeah, now you see this S here. means it's suspended. And then given the code we contributed to we made to the Slurm. Oh yeah, here is just showing you in the dashboard the VM is suspended as well. And given the code that we made to the Slurm, the node, actually the state will change to the suspended state as well. And now let's imagine that we decrease the cloud utilization to below the threshold. So now the job should resume and back to the running state within the moment. As you can see here, it's back to the running state and the times keep counting. So that's pretty much the end of this demo. We'll go back to the Horizon dashboard and show you that the VM is actually back to the active status again after we decrease the utilization. If you refresh the page, yes, okay. Let's go back to. Okay, so coming next, Raju gonna talk about the future work we're gonna do.
Thanks, Lucas. Our next steps to this project is we want to harden up the UI that we have. It's called Giji, and so we have a very minimal strategy included into the watcher right now, and we'd like to add more aspects or more parameters to it with different combinations so that we could have an optimal placement of creation and placement of the VMs. Apart from this, we want to add another strategy that could place the VMs taking into consideration the actual cloud workload and the HPC jobs that comes in. It's assumed whatever the cloud users they come in, they assume it's going to be some kind of overcommitment of the resources, but still it's something that we are looking forward to explore into, and how this overcommit causes and how it affects the actual cloud workload when we run HPC, these compute jobs and the cloud workloads together on the same node, and if they are sharing some resources. And apart from that, we would be working on testing and hardening of the Slurm code that we made changes to, because we had the minimal thing working, but there are some side effects to it, and it's still to be figured out and improved and worked upon. So in order to summarize it, we had these goals. We wanted to manage the sharing of resources, for which we used OpenStack Watcher. We added a new strategy that will drive the elasticity of the cluster, growing and shrinking it based on the cloud utilization. Now I wanted to have this shrinking of the cluster in a workload preserving manner, for which we use the we leverage the feature of OpenStack, and that we can suspend the VM to hold the state, and we added a new state in Slurm to manage these suspended instances. And we wanted to have a simple user experience, for which we added Giji. So in order to conclude, if we have this implementation running, we could have a better throughput on HPC cluster, as more and more jobs could be executed based on the resources that are added to it dynamically, rather than just working on a static set of nodes. And another reason could be we could have a better resource utilization, because most of the nodes were just lying idle as of now, which could be used by the cloud workload to get more things done, and you have a better or an overall better resource utilization of the cluster. So this is all I have for now. Thank you. Any questions?
I think we have a couple minutes here for Q&A.
Go ahead.
Yeah.
When users set a wall time, they expect, say, a job to last exactly 24 hours. If that, you then need to shrink the cluster and suspend that job.
Mm-hmm.
Then if you then suspend it for 12 hours and then you start it up again, next time they're going to ask for a wall time of 12 hours plus another 15. judging the wall time, but then of course your wall time gets extended.
So,
I'll take that.
go ahead.
Yes, so when we suspend the node and we change the state of the node as, like, if we suspend the job and we suspend the node, the clock doesn't refresh, like it stays there. And from whatever time you begin with, it'll count, like it'll resume from that very point, and probably it won't include the time for which it was suspended. So the execution time, it remains, like, we get rid of that suspension time.
So you artificially extend the wall time for their...
Yes, yes.
I don't think that's artificial, that's part of Slurm. There are already suspension mechanisms in Slurm where if a job is preempted or suspended, the wall time clock just stops.
Yeah, it won't include that suspended time into your, like the wall time or wall period, whatever you have.
Yes?
So what happens if I submit a job or a bunch of jobs that only take an hour, say,
Mhm.
and then they get suspended halfway through, and they could potentially get suspended for days, right? So when do you make the call? It's just quicker to kill them and run them again.
So basically, if you think about that, right? I mean, the scenario you said, I mean, if you use the resource from the cloud, it's unlikely. I mean, the possibility that happen going to be low because it's comparing to HPC cluster, which always fill up. You always have 100%. But we count on the statistic that we have seen so far that in the cloud, you always underutilize your resource that you have.
But so an example, particularly for high-throughput computing,
Yeah.
you might want to do a parameter sweep job. I want to spin 100 jobs, each of which only run for an hour.
Right.
So I submit all those, and a whole bunch of them run on the cloud. Eventually, they probably run churn through. But you know, a couple of them get sent to the cloud and then get suspended, and then.
But if I understand correctly, right, the HTC job, one of the characteristics is that it is an independent job, right? I mean, you run by itself. It doesn't depend on, even with 100 jobs, right? So if you get a couple of jobs done working, it doesn't mean that you cannot submit the other 98 jobs in the HPC cluster once it becomes available. All this is about the idea of you add on more resource to your HPC cluster. And the virtual HPC cluster that we have in the cloud, the reason we came up with it, actually, it was one of Raju and Vinay's ideas. And we thought that it's one way to utilize what you have in the cloud. And then you have a separate HPC cluster, which is totally different from what you have existing physical HPC cluster. So those two are totally separate.
Yeah, it's a good idea, but just
And
where the suspension thing might be.
right, if you go back to the future work, that's one of the things that Watcher is great for. I mean, anything complicated like that, right? I mean, we could put in more strategies. What we have here is very simple strategy, less than, greater than, equal to 50%. Then something like that happen, and again, I could see this in a different environment. You will have a different strategies altogether, depending on utilization of your HPC cluster, the existing one.
So my understanding is when you set the Slurm job to suspend, you use the Slurm preemption mechanism and made a call into the Slurm controller to request it?
So it's not exactly a Slurm preemption. Like on the Slurm, it will just suspend the job and you update the node state. We're not.
Sorry, just dealing with only the job state.
Mm-hmm.
I actually don't know how to suspend a Slurm job other than preemption. So I guess I'm asking the question. But I'm also asking the secondary question, did you consider using the checkpoint instead of the suspend so that it can be requeued to a different node?
Okay, so if you just want to suspend a job, there is an API. It's already there. You can, as an admin, you can do a S control suspend and the job ID. It will suspend the job. There's no like feature of suspending a node, so that is what we added. And coming to the checkpointing thing, so yes, you could checkpoint it. It will be easier, but it will have you'll have to make some more provisions for it. And we just wanted to keep things simple. And for that, we use the existing feature on OpenStack Cloud. Yes, you could do this. Like if you want to move from one node to another and want to save the state, yes, checkpointing could be an option.
Conversely, once a Slurm job is suspended and the Slurm instance is therefore not utilizing any CPU, is there any reason to terminate, suspend or terminate the instance rather than just running it oversubscribed on the cloud node?
We like to keep the state of the, like if we had used checkpointing in order to keep the state of the job, then yes, we could, like if that specific VM fits somewhere, yes, you could use that or we could reuse it. But we wanted to keep the state of the job, and suspending the VM was the only option that we had, like just to keep things simple. We suspended the job, and we need to suspend the job in order to release the resources so that a new VM could be created on those resources.
That's what I'm wondering about. Did you need to suspend or terminate the VM to release the resources? Because it's not using CPU. The QEMU image is going to be swapped out to swap space because it's not accessing RAM. And the second VM can be running on a hypervisor without impacting the first.
There is a limitation with OpenStack. It won't allow you to create new VMs.
You oversubscribe CPUs quite easily. I mean, our policy is not to oversubscribe RAM, but I understand that you can attach enough swap space that you will be able to oversubscribe physical RAM.
But yeah, even for oversubscription, you have a limitation, right? You can't subscribe it more than a specified limit, is what my understanding is. Like,
I think yes. I think we get your point there, and that's probably something that we want to hardening and then figure out. I mean, this is real beginning. We have like 2 or 3 people working part time on it, but no, point well taken. Yep, definitely.
Sure.
Any more questions? Great, thank you very much. If you have any questions come up, we're more than welcome to answer any questions you may have. Thank you.
Thank you.